Hi everyone, this is Dr. G. Ravindranath Reddy working as Assistant Professor of Mathematics in MLR Institute of Technology, Hyderabad. So we are discussing the numerical methods and integral transform course. In that course, we are at the inverse Laplace transform, how to find out the inverse Laplace transform using partial fractions. So in this video, we will discuss how to find out the inverse Laplace transform using partial fractions technique. So in the previous video, we have seen how to find out the inverse Laplace transform for the simple functions by using our basic formulas in the inverse Laplace transform. Now we will go for the next two techniques by using partial fractions. So partial fractions is a powerful technique which is used to simplify the complex rational functions. So whenever we are having a function in the form of p by q or this g bar of s by h bar of s, then we can find out this f bar of s value. Whenever this f bar of s is in this form, then if you want to find out the L inverse of this type of functions, then we can take the help of this partial fractions technique. So this partial fraction technique is used to simplify a complex rational functions, making them easier to handle when finding the inverse Laplace transforms. Okay, whenever the given function is in this form, g bar of s by h bar of s, or we can call it as a rational functions, then in order to find out that inverse Laplace transform for the rational functions, we will convert that rational functions into a simple easier functions to handle or to find out the inverse Laplace transform. By breaking down a function into a simpler fractions, you can utilize known Laplace transform formulas to apply this inverse Laplace transform for the given original function. That is the main use of this partial fractions here. So for example, I have taken a function f bar of s which is in this form. Now I want to find out the inverse Laplace transform for this function which is of the form g bar of s by h bar of s, where g and h are the polynomials in terms of s. Then f bar of s can be obtained by resolving f bar of s into a partial fractions. After converting into a partial fractions, we can apply inverse Laplace transform term by term, and we can take the help of our standard formulas, and we can find out the inverse Laplace transform for the given rational functions. Now, how to solve this? How to split into a partial fractions for the given function? So, this is our rational function f bar of s, and where the numerator and denominator are polynomials. So use the partial fractions technique to rewrite that f bar of s as a sum of simpler fractions with fractions from the denominator. So let us take, suppose, so f bar of s here he has given us f bar of s is equal to 2s plus 3 by s square plus 4s plus 4. This is the given function he has given. Now here you convert this into, we have to, in order to find out this inverse Laplace transform for this one, we can rewrite this function as 2s plus 3 by s plus 2 whole square. So directly if we apply inverse Laplace transform, we don't have any formulas here. So now we have to convert this function in the form of simple formulas like 1 by s plus 1, s plus a, or 1 by s plus 2, or something into our standard formulas here. Now we will see how to, in order to convert this function into a simple function, sum of simple functions or simpler functions, then we have to take the help of this. How to convert this by using this partial fractions technique we are going to discuss here. Now here we are having different types of denominators. Suppose if the denominator is a linear factors, for example if we take f bar of s is equal to 2s plus 3 by s plus 1 into s plus 2. Then now our task is we have to convert this function into a partial fractions. How can you convert this? We will discuss. So now, whenever the denominator contains this type of linear factors, then we'll have the term of the form. This is our form here. Then we can take. So suppose if the denominator is in this form s minus a, then we have to take a by s minus a. Suppose if we have 1 by s minus a into s minus b, this is our function. Both denominator having two linear factors. Now if you want to split into a partial fractions, then we can take a by, you can take any one of these two factors here, s minus a, plus we are having another factor, so we can take b by s minus b. So whenever we are having a linear factors in the denominator, then if you want to convert that into a partial fractions, this is the procedure we have to follow. A by s minus a plus b by s minus b. Suppose we are having one more factor, s minus c, then we have to take c by s minus c. So this is the way how we can split this. And now our task is finding the values of a, b, c. We have to get that value. So after finding that, if you replace that a value, b value and c value in this, then this entire function will be converted into a simpler functions. So directly we can apply inverse Laplace transform. Then we can use our standard formulas. We can find out our inverse Laplace transform for the given function. This is the advantage of this partial fractions here. So in this partial fractions, this is the case 1. So whenever we are having the denominator as a linear factors, product of linear factors, then this is the way how we can split into a partial fractions. That is the first point we have to remember. And the second point is, suppose if it is a linear factor is good, and that linear factor is repeated. So in this example, in the first example, s minus a, that is a linear factor, that is not a repeated, so it came only one time. S minus b is a linear factor which is also not repeated, and s minus c is also linear factor which is not repeated. So even though we are having a linear factors and that linear factors are not repeated, then we can follow this. Suppose if the linear factors are repeated, for example, s minus a whole square. Now if you want to split this s minus a, which is a linear factor, and since you are having the power for that s minus a is 2, that means it is repeated twice. So whenever we are having a linear factors which are repeated, then if you want to convert this into a partial fractions, then we can take this as a standard form, a by s minus a. First time we have to consider, and next one b by s minus a whole square. And suppose if it is repeated thrice, then we have to take c by s minus a whole cube. And suppose similarly like this, as the power of that linear factor is increased, then we have to take number of terms. If it is repeated thrice, then here we will get 3 terms. One in the denominator of the first term is s minus a, the power is 1, and the denominator of the second term is s minus a whole square, the power is increased by 1, and in the denominator of the third term is s minus a whole cube. As the number of terms increases, the power of the denominator is also increasing. That must be similar to this power. So this is the way how we can take these repeated factors in order to split that one into a partial fractions. So s minus a whole to the power of n, if you have like this in the denominator, then we have to take 1 by a by s minus a, b by s minus a whole square, plus c by s minus a whole cube, and so on up to we have to take that power n. Okay, this is our case 2. And now suppose if the denominator is, we don't have the linear factors in the denominator. Suppose if the denominator is not possible to split into a linear factors, or if the denominator is a quadratic polynomial which is not reducible into a linear factors, then how can you find out that? How can you split that into a partial fractions? So irreducible quadratic factor. So this, if suppose if you are having denominator s by 1 by s square plus bs plus c. So this is our quadratic polynomial or quadratic factor, which is not possible to reduce into a linear factors. Which is not possible to reduce into a linear factors. So whenever it is quadratic polynomial which is not possible to reduce into a linear factors, then if you want to split this function into a partial fractions, this is the procedure we have to follow. A s plus b by that factor which is not reducible into a linear factor. Suppose we will take one example for this one so that you can understand this. Suppose we are having 1 by s square plus 2. S square plus 2. This is a quadratic polynomial or quadratic factor which is not reducible into a linear factors. So now if you want to split this one in this linear partial fractions, then we have to take this one as as plus b. So why we are taking s here? Because the function is in terms of s. So we have to take as plus b by s square plus 2. And similarly, for suppose s square plus 3s plus 7. If it is not reducible, then we can take this as as plus b by s square plus 3s plus 7. So this is the way how we can apply this one. So these are the three cases we have to remember before applying the partial fractions. And now one more very important thing to apply the partial fractions is, suppose if the given function is of this form g bar of s by h bar of s. So now suppose if you want to apply the partial fractions for this function, the condition is the degree of g bar of s, the degree of the numerator always must be less than the degree of the denominator, that is h bar of s. Okay, that is the important point we have to remember. So the numerator degree always less than the denominator degree, then only it is possible to split into a partial fractions. Suppose even both degrees numerator degree and denominator degree, even though they are equal, then it is not possible to convert into a partial fractions. Even though if you have a greater than, the degree of the numerator is greater than the degree of the denominator, then splitting into a partial fractions is not possible. Then how can we apply for partial fractions for this type of functions? Then first we have to apply the normal division. First we have to apply the normal division for this, and then we have to convert into this condition, and then we have to apply partial fractions. That is the condition we have to check. So by blindly it is not possible to apply the partial fractions for all the functions. This condition has to satisfy. The degree of the numerator should be less than the degree of the denominator. For example, suppose if you take s plus 1 by s square plus 2s plus 3, then we can apply the partial fractions for this one, because the numerator degree is 1 and whereas the denominator degree s square, the highest degree term is s squared, so the degree of this denominator is 2. So this condition will satisfy, so that we can apply this split into a partial fractions. So that is the important point we have to remember. Now let us take the concept of partial fractions, and now we will see how to find out the inverse Laplace transform for this function. So 3s plus 7 by s square minus 2s minus 3. So whenever we are having a quadratic factor in the denominator, first we have to check whether is it possible to split into a linear factors or not. if it is possible to split into a linear factors, then we can go for the partial fractions, because in the numerator the degree is equal to 1 and the denominator having the degree 2. So the numerator degree is less than the denominator degree. So that partial fraction condition satisfies for this function. So we are ready to apply this for this function. This partial fraction concept is applicable. Okay, now let us take this function. So now we know how to find out the factors for this quadratic polynomial. So you apply this s square minus 2s minus 3. So this can be written as s square 3s plus s minus 3. Find out the factorization method. So by using this factorization method, we can get our factors as s plus 1 and s minus 3. So these are the linear factors. So this can be written as 3s plus 7 by s plus 1 into s minus 3. So for this we got the linear factors. Now convert that into a linear factors now. So both are linear factors, so we have to apply case 1 here. So this is our case 1 property, linear factors. Whenever the denominator contains the linear factors, then like this we have to write into a partial fractions. So a by s plus 1 plus b by s minus 3. Now our task is we have to find out this a value and b value here. So now we'll take some shortcut methods to find out the a value and b value whenever we are having a linear factors. Now listen carefully. Now I want to find out the value of a. So now if you want to find out the value of a, then whatever the denominator we are having under a, you equate the denominator to 0. You will get s plus 1 is equal to 0. So from this you will get s is equal to minus 1. So now remember this, s is equal to minus 1. Now go to the LHS part here. So this LHS part can be written as 3s plus 7 by s plus 1 into s minus 3. Now what we have to do is, whatever the factor we have equated to 0 on the RHS side, you neglect that factor in the LHS side, and for the remaining you substitute s is equal to minus 1. So if you substitute s is equal to minus 1, you will get minus 3 plus 7 by minus 1 minus 3. So you will get 4 by minus 4, you will get this value is equal to minus 1. So you will get a is equal to minus 1. Okay, like this we can find out. And similarly, now I want to find out the value of b here. I want to find out the value of b. Now whatever the factor we are having under b, you equate that factor to 0. Our factor is s minus 3 is equal to 0, and from this you will get s is equal to 3. Now go to the RHS. Our RHS function is 3s plus 7 by, so this can be written as s plus 1 into s minus 3. So whatever the function we have equated to 0, you neglect that function, you neglect that factor in LHS side. After neglecting that, you will get 3s plus 7 by s plus 1. Now in this you substitute s is equal to 3, we will get our required one. Okay, that is one shortcut procedure we can use whenever we are having a linear factors in the denominator. So like this we can find out that. So we got a is equal to minus 1 and b is equal to minus 1. So b is equal to 4. Now after finding that a value and b value, so here we have another procedure here. Now if you want to find out the value of a, so first we can also follow this procedure. Take the LCM here. So a into s minus 3 plus b into s plus 1 by the denominator s plus 1 into s minus 3. So this s plus 1 into s minus 3, this gets cancelled. So you will get 3s plus 7 is equal to a of s minus 3 plus b of s plus 1. Now I want to find out the value of a. In order to find out the value of a, the b term must be equal to 0. We have to neglect that b term. So we have, in order to get this second term equal to 0, this is possible only by substituting s is equal to minus 1. So put s is equal to minus 1 on both sides. So you will get minus 3 plus 7 is equal to a into minus 1 minus 3, and this term becomes 0. So now simplify this, 4 minus 4a. So this gets cancelled. You will get a is equal to minus 1. And similarly, if you want to get the value of b, this term must be 0. So in order to get this term equal to 0, we have to take s is equal to 3. Put s is equal to 3 in both sides. We can get our b is equal to 4. This is another way. We can also find out this a value and b values here. So once after finding that a value, b value, you substitute that values here. A is equal to minus 1, b is equal to 4. Now this function, this entire function is converted into a simple function. How can you say that this is a simple function? Because the denominator we are having in the form of 1 by s plus a. Here in the second term we are having 1 by s minus a form. So for this we have the standard formulas to find out the L inverse here. Then we are ready to apply L inverse on both sides. So L inverse of this plus L inverse of linearity property. You take this minus sign outside. Minus 1 into L inverse of this, plus 4 is constant, so we can also take 4 into L inverse of s by 1 by s minus 3. We have the formula. For this we can take e power minus 80, and for this we can take e power 80. So this can be written as minus of e power minus t plus 4 into e power 3t. So if you have positive sign, then the power of that exponential function becomes negative sign. If you have negative sign, then we will get a positive power for the exponential function. So this is the way how we can use. So by using these partial fractions, we have converted this bigger function into a smaller form. Sum of easy functions, simpler functions, and then apply this inverse, we will get our required L inverse for the given function. So by using this partial fraction technique, we can also find out the L inverse for the complex functions also. This is one best example how we can apply these partial fractions here. Now we will take another function. So in this function, we have the linear factor. That linear factor is repeated twice, s plus 1 whole square. S plus 1 is a linear factor. The power of that s plus 1 is 2. So linear repeated. And the second factor is s square plus 1. This is a quadratic polynomial, quadratic factor. So which is not reducible into a linear factors. Now we will see how to find out how to split into these partial fractions here. Take this. So we have taken, whenever the factor, linear factor is repeated twice, then we have case 2, how to express that into a partial fractions. That is a by first s plus 1, one linear factor, and plus b by that same linear factor repeated twice, so we have to take s plus 1 whole square. So we are having s plus 1 whole square, so we have to take 2 terms here for the linear factor. And the next one factor is s square plus 1, which is not possible to split into a linear factor. So we are having already a, b is completed, so now go for c, cs plus d by s square plus 1. So now our task is finding a value, b value, c value and d value here. We have to find out all these 4 values. If we replace that a value, b value, c value and d value in this, then it will be converted into a simple functions. So similarly, take the LCM and cancel the denominator on both sides. So finally you will get this one. So how can you take this LCM here? So this can be written as our LCM is s plus 1 whole square into s square plus 1. Go to the numerator a. So we are having only one s plus 1. So we here in the denominator we are having s plus 1 whole square. So we have shortage of s plus 1. And here we don't have s square plus 1 in the denominator. So you take that plus b into. So s plus 1 whole square we are having the denominator. So you cancel this. The remaining one is s square plus 1 plus cs plus d into. If you cancel this s square plus 1, the remaining one is s plus 1 whole square. So we can cancel this, we can cancel this. This is our remaining term after cancelling the denominator on both sides. Now what we have to do is, so equating the coefficients of s cube. Now remove these brackets. So you will get s cube terms here. So now equate that s cube terms. If you equate that s cube terms here, in the LHS side you will get only two s cube terms which contains a and c. So in the RHS side, this side we don't have s cube term. So we can convert, we can take that value is equal to 0. So a plus c is equal to 0. You will get one equation by equating coefficients of s cube on both sides. Now go for s square coefficients. So you will get a plus b plus 2c plus d equal to 0. So here we don't have s square term also. So we will take that coefficient of s square is equal to 0 here. And similarly go for s terms, coefficients of s terms. You will get this. Now our task is we have to solve these 1, 2, 3 equations to get the values of a, b, c and d here. So how can you solve this? Let us see once. So now put s is equal to minus 1 here. Suppose if you go for the previous slide here. Now suppose if you substitute s is equal to minus 1 in this entire equation, this entire one. So you will get, so if you replace s is equal to minus 1, this term becomes 0 and this we can really eliminate. And here also if you replace s with minus 1, so this term also get cancelled. So the only term is b of s square plus 1 is equal to s. Now let's replace that s is equal to minus 1. So if you replace s is equal to minus 1 whole square plus 1 is equal to minus 1. So b of minus 1 whole square, that is 1 plus 1 is equal to minus 1. So 2b is equal to minus 1, b is equal to minus 1 by 2. So that is the thing what we have done in the previous one. By substituting s is equal to minus 1, we got b is equal to minus 1 by 2. Now you substitute that b values in the equations to get the remaining a value, b value, d value and c value here. So substituting 1 in equation 3. You substitute that equation 1 in 3. What is our equation 1 here? A plus c is equal to 0. So if you replace a plus c equal to 0, you will get 2d is equal to 1. From this you will get d is equal to 1 by 2. Now we got d value also here by substituting. So d is equal to 1 by 2. Now we got b value and d value here. Now our task is finding a and c value here. Now we'll see how to get that values, remaining two alphabets values here. Substituting the values of b and d. What is our b and d? B value, d value in equation 2. So in place of b substitute this, in place of d substitute this. So finally you will get a plus 2c is equal to 0. Now take this equation 1, a plus c is equal to 0. Subtract this, you will get c value here. So you will get this equation. Already in the first equation we are having a plus c is equal to 0. Now you solve these two equations, you will get both A value and C value is equal to 0. Now A equal to 0, B equal to minus 1 by 2, C value equal to 0 and D value is equal to 1 by 2. Now you substitute that values here. We will get this entire function is converted into this form. Now apply both sides L inverse. Take 1 by 2 common here, 1 by 2 of this first term, 1 by s square plus 1. So here we are having minus, so I have taken this term as the second term here, L inverse of this. Now for this we have the standard formula, L inverse of 1 by s square plus a square. This can be written as 1 by a into sin 80. Okay, and similarly we are having 1 by L inverse of 1 by s plus a whole square. So for this we have to apply the first shifting theorem, which is not discussed. We can discuss in this next video. So by using this we will get our required value here. So this is our inverse Laplace transform for this one. So the important thing is, whenever the denominators as linear factors or quadratic factors which is reducible into a linear factors, then we don't have any problem. If it is not reducible into a linear factors, then we have to follow the procedure as we mentioned in the case 3. So this is one of the technique in order to convert that complex functions into a simpler functions and then to find out the inverse Laplace transform. So in this video we have discussed how to find out the inverse Laplace transform by using the partial fractions. Now in the next video we will see the property of this inverse Laplace transform, that is first shifting property, and when we can apply this first shifting theorem in order to find out the inverse Laplace transform. In which case we can go for the first shifting theorem. We will discuss all these things in the next video. Thank you.